Good morning, students. Welcome to the class on NMR spectroscopy. We are discussing advanced topics in NMR spectroscopy. Today we will discuss second order spectrum. What is second order spectra or what is first order spectra? I'll give you a simple shortcut. If we can expect the multiplets for different protons based on n plus 1 rule, then it is a first order spectra. That means if the spectra is according to the principle, whatever we have learned so far, we can predict the splitting pattern of each and every proton, then it is a first order spectra. But if we cannot do that because of complex multiplets, if the spectra is giving complex multiplets, so it is a second order spectra. The complex multiplets needs theoretical mathematical calculations to interpret. Of course, we are not going to do that, but in fact, they need theoretical mathematical calculations. Right. How do we say whether it is a first order spectra or second order spectra? For the same J value, if a compound or if two protons are giving large delta differences, that means we can say weak coupling. There is a weak coupling between the signals of these two protons, then it is called first order spectra. It is first order spectra. In terms of numbers, the delta difference between these two divided by coupling constant, if it is more than 6, it is a large value. If it is more than 6, it is a first order spectra. So to get a constant, what we will do, we will also represent the delta values in frequencies, in hertz. J value we measure in hertz. So for calculation purpose, what we will do, we will represent the delta values also in hertz, so that hertz and hertz will get cancelled. We will get simple numbers. So if the chemical shift difference between these two protons divided by J value, coupling constant of the multiplet, in this multiplet or in this multiplet, if it is greater than 6, it is a first order spectra. Or for the same J value, that means we are not changing the J value. If these two protons are giving signals with a very low delta difference, that means here the delta difference is very, very small. Or in other words, what we can say, there is a strong coupling between these two signals. Then we call it as second order spectra. In numbers, what we will say, the frequency difference or delta difference by J value is less than 6. It is the small. So it is a general condition, okay? We will take the delta also in hertz. Of course, J is expressed in hertz. So the delta difference between the signals, these two signals divided by J, if it is more than 6, it is called first order spectra. If the delta difference between two signals expressed in hertz divided by J value is less than 6, it is second order spectra. Even this 6 is not a constant value. It may change also. It depends on a particular compound. Now we will look at the second order spectra. Of course, so far whatever we have learned, they are first order spectra. Now we will look at the second order spectra. So before going to second order spectra, we will look at what is spin system. In the second order spectra, we give labeling of protons based on the delta values. So based on the delta value differences, for example, if we have two different protons which are giving two different signals and the delta values are very similar, or in other words we can say if they have very small delta differences, then these two signals are very nearby, then we call it as, we label it as A, B. If we have three, we will label them A, B, C and so on. Then the number of protons is given by, for example, if we have two A type protons, we will label it as A2. If we have three B type protons, we will label it as B3. If we have four protons of C type, we will label it as C4. So it is something like this. So when we will give ABC labeling, when these protons are having similar delta, or in other words we can say their delta differences between these two signals is very small, then we will call it as, then we will label it as, each proton is labeled as A type, B type and C type. Alternatively, if they have large chemical delta differences, each chemically different proton gives different signals with a large delta difference, then we will label them as A, B, C and so on, and X, Y, Z and so on, because they have different delta value. Why we are using these notations? You see, in alphabets, A, B, C are the starting letters, whereas X, Y, Z are the ending letters. That means there is a huge large separation between the first letters and large last letters, because they have large differences. Similarly, the protons which are exhibiting large delta differences, they are expressed as ABC, XYZ. For example, if there are three different types of delta values, then we can label them as ABC and so on, then middle letters M, N, O, middle letters, and then there is a difference, and then we will label it as XYZ. Okay, so these are generally second order spectra. Sorry, this is first order spectra and this is second order spectra. So when the delta difference between two similar protons or two different protons is very small, then we don't see the multiplets according to n+1 rule. They become very complex, so they give second order spectra. When the delta differences are very large, their signals are very clear, and we can expect the multiplicity using n+1 rule. So these are first order spectra. Now I will give some notations. What is AX? AX, as I said, it is a first order spectra. Then what are A and X? A is one type of proton, X is another type of proton, whose delta differences, that means delta of A and delta of X protons, they will have large difference. What is AB? As I said, because they are very close, the A type protons and B type protons delta values are very close. Their multiplicities are complex, so it gives a second order spectrum. Then two protons have similar delta value, or in other words, we can say the delta difference between these two protons is very small. Then we also have A2. What is A2? What is A2? There are two different protons, but they have similar delta value. There are two different protons, but they have similar delta value. Or in other words, we can say there are two different protons which are chemically equivalent and magnetically equivalent. When two different protons are chemically equivalent, then we will get only one signal instead of two. So if there are two such protons, two such chemically equivalent protons, we will label it as A2. If there are three such chemically equivalent protons, we will label it as A3. If there are four such chemically equivalent protons which are giving only one signal, then we will label it as A4. So it is depend on the number of chemically equivalent protons. Then what is A and A dash? They have identical delta value, but they are magnetically non-equivalent. Magnetically non-equivalent. They are chemically equivalent but magnetically non-equivalent. So the coupling constant values will be different for A and A dash protons. And because we have A dash, it represents two protons. Similarly, we have AMX where three widely different protons. Chemical shift difference between A and M will be different, will be large. Similarly, chemical shift difference between M protons and X protons is also large. So because they have three widely different protons, we label it as AMX. What is ABC? Again, we have three different protons, but their chemical shift values are very similar. They're very close together. So this is called ABC. We will take some simple examples. Then we will discuss AX. What is AX type protons? For example, if we have two protons in the molecule, we can label them A and X. This is A type protons, this is X type protons. When we will label them as A and X, when they have large chemical shift differences. If the spectra is very clear, because this proton is having one alpha hydrogen, so based on n+1 rule, it gives a doublet. Say for example, if it is for A type protons, if it is for X type protons. Similarly, this X type proton is also having only one alpha hydrogen, so according to n+1 rule, we get a doublet here. So that means if the spectra is very clear, then we will call it as first order spectra. First order spectra. When we have clear spectra, we can also measure the delta values very clearly. For HA, we will take the delta exactly at the middle of the multiplet. Exactly at the middle of the multiplet. Here also we will take delta exactly at the middle of the multiplet. So this is delta for A type proton, this is delta for X type protons. And if we want average, we can take average also. It is delta A minus sorry, it is a middle value. Okay, so we can take that value also. But when it is AB type, when it is AB type, what will happen? Again, we will have two different protons. One is A type proton, one is B type proton. But their chemical shift difference between these two signals, it is very, very less. For example, if it becomes like this, if it becomes type, if it becomes complex type, then this is a second order spectra. It is a second order spectra. Why it is called second order? Yeah, we have A type proton here. It is having one alpha proton, so according to n plus 1 rule it should give a doublet, but we don't see a clear doublet here. Similarly, B also, this is for H here, this is for HB. Similarly, B also, it should give a doublet, but we don't see a clear doublet, right? These two signals, because they have very small delta difference, they are mixing with each other and they are giving a complex multiplet. Generally, we may confuse that it may be a quartet, right? But it is not a quartet. It is a doublet and doublet of A protons and B protons, which is mixing with each other, which is interacting with each other. As we know, if these two are strongly interacting, then we can expect skewing effect. That means the inner peaks will increase their intensity, outer peaks will decrease their intensity. So skewing can also be observed in case of second order spectrum. I'll give you one simple thing. When we apply low magnetic field, we generally observe second order spectra, but when we apply high magnetic field, we observe first order spectra. Because, so for example, take 60 megahertz instrument, because it is having very low magnetic field, it may not, the spectrum may not be very clear. So in that case, what we will say it is a second order spectra. But the same compound, when we take it on a high magnetic field, say for example 300 megahertz or 500 megahertz, then the spectrum becomes very clear. Under high magnetic field, the spectrum becomes very clear. Then we will say it is a first order. So if the spectra is, if the multiplets are not interpreted, it is a second order spectra. But if the multiplets are interpreted according to the n plus 1 rule, it is a first order spectra. Now, if we want to calculate the delta value, how do we calculate the delta value? Yeah, this is the coupling constant value, and this is again a coupling constant value. Generally, for any peak, what we will do, we will take the delta exactly at the middle of the multiplet. But here we cannot take the middle of the multiplet. Why? Because it is AB type system where this doublet is different, this doublet is different. This doublet belongs to A type protons, this doublet belongs to B type protons. So if you take the middle of the delta, we will have only one delta. We don't get A type protons delta, B type protons delta. Generally, in the complex systems, what it will do, the delta is not exactly at the middle. Say, for example, if it is different individual doublet, if this is also individual doublet. If we think in this way, then what we try to do, we will try to take the delta value exactly at the middle of the two peaks, right? But in the second order spectra, the delta value is almost closer to the inner peak. So it is not exactly at the middle, it is closer to the inner peak. Yeah, I will try to draw again. sorry. So generally we try to predict the delta at the middle, but it is not the predicted delta. Why? Because this is for A type protons, this is for B type protons. It should be different for these protons and these protons. Then if you consider this is the HA type protons, A type protons, then what we will try to do, we will try to predict the delta at the middle, right? Generally we will take the middle of the multiplet as the delta value, but in this case, in the second order spectra, we cannot take the delta exactly at the middle. The delta value will be closer to the inner peak. Delta value will be closer to the inner peak. Then how do we measure delta A and delta B? There is a mathematical calculation for this. What we need to do, we need to take the delta A and minus delta B. How do we get this delta A minus delta B? The frequency difference or delta A minus delta B can be obtained by delta 1 minus delta square root of delta 1 minus delta 4 multiplied by delta 2 minus delta 3. What is delta 1? This is delta 1, delta 2, delta 3, delta 4. The frequency values. So from this formula we will get the delta A minus delta B difference. Okay, then we can also point the middle of the multiplet. Okay, this we can easily point out. Okay, this we can easily get the middle of the multiplet value can be easily obtained from the spectrum, not a problem, right? Then what is delta B? What is delta A? Delta A value will be center or middle delta. So this is center, right? This is center delta. So center delta plus half of delta A minus delta B. How we measure delta B? It is again center delta minus half of delta A minus delta B. Center delta minus half of delta A minus delta B. In a first order spectra, the two signals will be very clear. So we can clearly measure the delta A, middle of this multiplet, delta X, middle of this multiplet. But in a complex second order spectra, the middle of this multiplet, it does not belong to single proton, it belongs to A type protons as well as B type protons. So if you take the middle of the multiplet, it does not mean that delta A or delta B. So how we measure the delta? For example, if you take these two peaks for the A type proton, these two peaks for B type proton, we may try to take the middle of these two peaks for delta A, middle of these two peaks for delta B. But it is not true in case of a second order spectra. In case of a second order spectra, the delta of this peak, A type protons, will be closer to the inner peak. Similarly, here also the delta of this B type protons is also closer to the inner peak. Then how do we measure it? It is simple. First, we need to calculate the delta A minus delta B, difference between these two. How do we measure this? From this formula, square root of delta 1 minus delta 4 into delta 2 minus delta 3. So when we do that, we will get delta A minus delta B. Then what is the difference between these two? Middle center delta value and delta B. Then what is the difference between delta A and center? So delta A is obtained by adding half of delta A minus delta B to the center delta. Delta B is obtained because it is lower than middle. So minus subtraction by subtracting half of delta A minus delta B from the center delta value. Center delta value we can identify it from the spectrum. Okay, we will point out, we will indicate a middle point From the scale bar, we can measure the chemical shift. Please. Now we will look at AX type system. Generally for AX type, as I said, delta nu by J greater than or 6 because it is a first order spectrum. Right. So when we say AX, as indicated in the previous case, we have two protons, which one is indicated HA and HX. If it is a first order spectra, it will be very clear. It will give a doublet for A type protons. It will give a doublet for X type protons, and the spectra is very clear. Here the delta nu by J value is 15. But when we decrease this delta nu by J value to 6, it becomes complex. The delta difference, the difference between delta values will decrease. How we will decrease this value? J is always constant. So by changing the delta values, we can arrive at delta nu by J at 6. When we do that, what is happening? It is not a clear doublet like in the previous case. It becomes a little bit complex. Though these two doublets are looking clearly, but the separation, delta separation between them is very small, so they become little bit complex. Now we can say it is a second order. Here it is a first order, it is a second order. So in this case, the second order and first order transition is occurring somewhere between delta nu by J 6 and 15, somewhere between 6 and 15. So it is not fixed value, delta nu by J greater than 6 or less than 6. It is not a fixed value. It is a general value, but it depends on case to case. Then if we further decrease it to 1.5, then they become even more closure. They become even more closure. In this case, what we say, we call it as AB. See, we don't see individual doublets. We see only a single multiplet from two different protons. A multiplet corresponding to two different protons. So then we call it as AB. If we further decrease it to 0.5, what will happen? The multiplet becomes even more complex. In the sense, a new multiplet becomes stronger. If the difference is 0, then we can clearly see a singlet. That time it is called as A2. Why it is called A2? Because we have two different protons which are chemically equivalent. Then we call it as A2. If you have two different chemically equivalent protons, they don't split each other's signal and they will give single delta value. So we observe a singlet. Through all this transition, you clearly see center peak intensities is increasing gradually. Terminal peaks intensity is decreasing gradually. Okay, so the middle peaks, their intensity will increase. The extreme peaks, their intensity will decrease. Okay, so if the multiplet, here it is somewhat clear, it looks like doublet and doublet, but here it is not a doublet. The multiplet is somewhat complex, so we call it as the AB system. So when we are observing AB system, when delta nu by J is almost 1.5, delta nu by J becomes 0, that means it is chemically equivalent. We don't get splitting or we don't get different delta values, we get only single delta value.